Hello. So what we're going to be looking at now is first order ODE theory. So previously we had seen how to solve differential equations and how to look at interval of existence and uniqueness based on the form of the solution that we found. What we're going to do is talk about some of the theory behind this. So the question is, just to remind you, is that we have an initial value problem. So it's a differential equation along with some initial condition. And we want to know, how long does this initial value problem exist as a solution? Is there even a solution? And if we go down a little further, we can see this visually. So if we have t naught here, why not? This initial condition here tells us that our function passes through this point. And how long does the solution exist? Well, we know in order for this differential equation to really make sense, we need the function to be differentiable. So we know that it's going to make sense in some open interval a to b. So I is from a to b. But then outside of this, we don't really know what's going to happen. Maybe the function blows up and then it has an asymptote. So it doesn't exist past, I don't know, 5 or something. And maybe when you go this way, it actually becomes vertical here. So the slope blows up, but the function doesn't blow up. So we can see maybe from 1 to 5, the largest interval maybe is 1 to 5 for this particular solution. But just from knowing that there is a solution, maybe we just want to say there is some open interval. We might not know exactly where it blows up, where the derivative ceases to make sense, things like that. But we just want to look at the theory, which is going to say how we can know that there is some region, there is some little portion of the ty plane where if you look only in here, the solution will make sense. You have a little window where the function makes sense, outside of which something bad can happen. So let's go down a little farther. And another question you can ask based on this sort of thing is, when does the solution exist uniquely? So maybe there is another solution that lives in here that also passes through this point. We'll see what that looks like in a second. So what do we know from this point, from what we've seen already? So we know that if the equation is linear, then you can find the interval of existence and uniqueness just by looking at the continuity of P and G. That's a very nice property of linear differential equations for the first order. Higher order too, but we haven't done it yet. If we can solve the differential equation, so the assumption is in this situation, this is so general we might not be able to solve it. But if we can't solve it, then what can we say? Well, we can explore what the interval of existence looks like just by looking at the solution. So if we had y is square root of 5 minus x, well, this right here is going to make sense when 5 minus x is bigger than 0. This function is going to be differentiable when 5 minus x is bigger than 0, which is the same as x, which is the same thing as 5 being greater than x, which gives us the interval negative infinity to 5. So x is always less than 5. So if you have a situation like this where you know what the function looks like as a function of y equals y is a function of x, then what you can do is you can analyze the existence interval by just looking at it. Another thing that you can do, if you know what it looks like, is that you can analyze the uniqueness of the solution. And this uniqueness is exactly related to whether or not solutions intersect. So let's see why this is the case. Suppose you have two solutions, y1 and y2, and you know that they intersect at some point, t star, y star. Then there are maybe two pictures you can think about. The first one is where these 2 points have the same initial condition. Because remember, these are solutions to the initial value problem. So, apologize for that. So if we have t star here, y star here, and this is our initial condition. Now let's just draw our two functions. Let's say this one is y1, and this one is y2. It's important to know that they have to have the same slope here, because the differential equation tells us that when you know what the value of t and y is, so y prime is f of t comma y. So they have to have the same slope here, because if you know what t is, that's this, and if you know what y is, which is this, then you can calculate what the slope is, which is whatever this thing calculates to. So they have to have the same slope, but uniqueness says, well, maybe they have the same slope here, but they're able to walk away still be different. And what, in terms of a story, if you think of y changing as a function of time, we say, suppose you start here, there isn't actually one way you could go. If you're going to go forward in time, you could walk this way, or you could walk upward. Or if you were going back in time, you were playing the movie backwards, you can go backwards like this, or you can go backwards like this. The non-uniqueness tells you that just knowing where you started doesn't tell you where you're going to go. That is when they cross at the initial condition here. Now, what happens if you have the initial condition over here, t star? I apologize. The crossing point, t star, y star is here, but they start off with different initial conditions. So let's start off with an initial condition for t1, y1. So this is going to be for the function y1. So suppose it's just going like this. And it passes through the point t star, y star. And then suppose that you have another solution. Maybe I'll pick a different initial condition. T2, y2. This is for a different solution. Walks like this, touches it, and keeps going. Maybe it crosses. Let's say it crosses. Okay, so let's just look at some examples we had. So if you look at this differential equation here, y prime is negative 1 over y times 1 over x times y. So you see from this differential equation that if you look at some solutions, so I'm going to sketch one right here. If you start here, it looks like you're going to go up like this. If you just follow the direction field lines, I'm just going to sketch a few. I'll pause it. You're back. So you see we have a few solutions here plotted. It's just approximates following the direction field. And the actual solutions are here. If you were to solve the differential equation, this is separable and linear, so you can use either of those methods to solve it. So when you get these solutions, you see that there's a problem at x equals 0. You can see that from all these solutions here. If you start here at -3, as you go forward, the function blows up. The same thing here. If you start here with initial condition 2, time 2, you can walk forward as long as you like. But when you walk backward, you're going to have problems at 0 because the function blows up. The same thing with the other initial condition. And so what you see is that x equals 0, there's a problem. But this x equals 0 problem can be seen from the differential equation itself. So this right here is f of x comma y. And then there's a problem. So f is not continuous at x equals 0. When you plug x equals 0 into here, it doesn't make any sense. And as x gets close to 0, this thing blows up. So there's something you can see just from the differential equation. You can see that there's going to be a problem. Let's go on to another example. This is the same example as above, except instead of a negative sign, there's a positive sign. So let's see what the solutions look like. So if you start here, you go down a straight line, basically. I'm going to pause and sketch a few. So for this differential equation, you can see the solutions. They're all lines passing through the origin. So there's two things to keep in mind here. If you start with an initial condition up here, the slope here is going to be infinite because so you have 4 here. So it's going to be 4, positive 4 over x. X is 0, and so this isn't going to make any sense. So here you can't even have an initial condition. And you can see all these points, the slopes are actually getting more and more vertical as you get closer and closer to the y-axis. That is represented in the fact that you can't divide by 0 here. The only time this right here can possibly make sense is when y and x are also going to 0. Basically, what you need is for this to make sense at this point here. One thing that also happens, it doesn't necessarily have to be the same, right? The point is that you need to get to 0 over 0 in some sense. And as a limit, it needs to make sense. Another thing you can see is the way I've written it, this point right here actually isn't allowed because you're not allowed to divide by 0. But if you rewrite the differential equation, it becomes a different one, but it's very much similar. If you write the differential equation like this, then x equals 0, y equals 0 is allowed because you're not dividing by 0 anymore. And so what you see is you can have a solution that starts here and then walks all the way up and passes through this point here. And the solutions are unique because in order to be a solution, it can't walk. Let me change color to see a little better. If you start here, you can't walk up here and then change your mind and go down this way. Even though this is a continuous function, and you start here and it is piecewise, it is a solution, it's not differentiable at this point. There's a corner. So you're not going to be able to go here and then jump off in a different solution. You have to continue going on the solution that you were on. And that's represented why you have this nice solution here. But you have to be careful because at x equals 0, all of these different solutions are the same for different values of c. So if you have y equals 2x and y equals negative 5x, when you plug x equals 0 in, they're the same. You get 0, 0. And so that is a suggestion that there's non-uniqueness. If you see this example up here, that we had the non-uniqueness where they cross, they, this cross right here, they cross like that. And then it tells you that the solution, the differential equation doesn't actually make sense here. Here, the solution differential equation does make sense because the slopes here are defined. So here, if you actually plug the t star and y star in, f gives you a definitive value. But for some reason, on one function, it's one value, and another function is different. And what that tells you is that f of t star y star doesn't actually make sense. It only makes sense when you take a limit, when you converge on it through some path here. So to continue what we were talking about below, let's see a slightly different situation where you have 2 over x. In this situation, you have the same sort of thing that can happen. The solution will only make sense when you somehow get a 0 over 0. It doesn't make sense here because the slopes are going to be infinite. But somehow you get solutions when they converge in like this. So I'm going to pause and try to sketch a few. So what you see here is when you sketch these, they look like parabolas. And they actually are. If you solve them, you will get a bunch of parabolas. And so if you start at some point, like around 2, 2, that's about here, you can go forward uniquely as far as you like. But once you go backwards, you hit this point right here, 0, 0. And then there's a problem. Because if you go here, apologize, when you go here, you can continue down this way, you can continue this way, continue this way, and all of these are going to all be solutions because the function is going to be differentiable here. They all have a slope 0 here. And if you were to start here as an initial condition, there's literally no way, there's no way to tell you which way you go, forward or backwards. You can go up this way, you can go through this solution, or this one. There's no restriction. And this comes from the fact that you have this differential equation here, this solution. You can have solutions like negative x squared. You have y is 0 times x squared, which is just this constant solution here. You can have y is 3x squared. And when you plug in x equals 0, they're all the same. You plug 0 into here, you get 0 and 0 and 0. And so they all cross through this point, and because they have the same slopes, then it actually, you can piece them together to form a solution. They're not going to be unique solutions though. So let's continue down to the next example. This one is the first nonlinear one that we've seen here. And I'm going to take pause and sketch some solutions. So we see here y prime is negative x over y. And we see that the problematic points come from y equals 0. And the only possible way that can get canceled out is x equals 0. And you see that there's not really any solutions here. Solutions would be like that. Regardless, on this part of the plane, the xy plane, you have problems. You have vertical lines here. So solutions aren't going to exist if they ever have to be forced to go there by the differential equation. And you see that they are forced to go there. Every single one of them seems to be forced to go downward. And that makes sense because the derivative up here is negative. And you actually have to look at the differential equation to really see that it has to be that way. One way to do that is to actually solve it, which you can solve it using separation of variables. You get solutions like this. See, the positive ones are in purple, and then the negative ones are in pink. And you see that this right here is going to make sense when c minus x squared is bigger than 0. And this is going to give you just an interval negative square root of c, square root of c. So in this case, you have this open, the closed interval is when the function exists as a function. It's a continuous function. But if you want it to be a solution to the differential equation, you're not going to allowed to have these infinite slopes here. So you're going to need an open interval. If you start here, then you need an open. I mean, you don't start here because infinite slope. Maybe you start here, then you can go down this way. You have an interval like this. You go forward this way. You have an interval like this. So your existence interval would be something like this. In either case, you see that the interval of existence really does depend on the initial value here, x naught, and also y naught. In this case, it doesn't depend on y naught. It doesn't depend on the sign of y naught. But if you started up here, the interval existence would be much longer. Something like that. Very rough sketch. In these cases, the existence interval didn't really depend on the y naught, and that's because the differential equation is linear. When it's nonlinear, it depends on the initial condition of x and y. Here is another example. So I'm going to pause and sketch some solutions. So you see here we have some solutions being plotted. So if you started up here, you continue up this way. So looks like existence and uniqueness would be forever. And the same thing down here. If you start here, then you can go this way, but then you have force to stop. And because the slope becomes vertical, the curves curve backward, but this curve right here isn't actually a solution to the differential equation. It's part of this solution here. This solution right here will include 4 of these branches. I mean, 2 branches, but each branch is made of 2 differential equation solutions. This is a solution here. This is a solution here. This is a solution here. And this is a solution here. The solutions have to be functions, and they have to be on a particular interval where you have passed through the initial value condition that the differential equation is given. So another thing that you can see is this weird particular point in 0, 0 where they cross. And that's where, again, 0, 0, 0 divided by 0. When y equals 0, that's causing these slopes here to be vertical. But here, that's where you have 0 divided by 0. And in theory, it might make sense that the function could pass through it. Not with this form right here, but if you wrote the differential equation as y prime y is equal to x, it's a different differential equation. Now 0 and 0 is allowed. So you could have solutions that pass through here. If you go backward in time, for this differential equation, they cease. They're not allowed to plug in 0 here. But for this one, you can pass through. But there is non-uniqueness. I mean, there is uniqueness actually, because they cross like this, they can't go down this way and then cut through this way because that gives you a corner. But you see that there is a potential for non-uniqueness because you're dividing by 0. It causes problems to exist. So let's go down to last example here. I'm sorry, there's a couple more examples. This right here is a blow-up example, which we'll sketch in a second. So here for this differential equation, what you see is there is blow-up. So let's see an example. So if you start here at 0, 1, you go backward as long as you like. It flattens out. But once you go forward, you see that you actually hit an asymptote. And that is captured in this right here. If you have the initial condition 0, 1, then you can just find out what the value of C is, and you can see what the point of where it blows up. So if you have -1 over x plus C, plug in 0, 1, it's -1 over C is 1, and the C is -1, so -1 over x minus 1 is y. That means where x equals 1, there's a problem. That's here, this line right here. It's not a solution, it's an asymptote, vertical asymptote. And the interesting thing about it is that if you just look at this right here has two parts. There's a part over here, and then there's a part over here. And each of these are separate solutions to the initial value problem. If you want an initial value point over here, then you get this part. If you get an initial value down here, then you get this part. And you can see that there are other types of problems that can happen. One thing that's very interesting is because this is an autonomous differential equation, you can actually take the whole picture, because the differential equation doesn't depend on time explicitly. You can take the whole picture and shift it over. Oh no, it's moving the picture too. Okay. Alternatively, you can move the picture in the background like that. And then you still get a solution to the differential equation. Like you see that it still has the same type of behavior. It still follows the direction field lines. It's because the direction field lines don't change when you vary x. So you get blow-ups at every single point, which makes sense here. Every point right here is going to give you a problem. The only one that won't give you a problem is when you're not allowed to use this form, when you have to use y equals 0. There's one solution here that exists for all time. It's this one right here. And you can see that there's uniqueness because these things don't pass. They don't cross each other. So it's interesting thing what happens when y prime grows like y squared, then it's much faster than something like this. This right here gives you exponential growth, but this right here gives you faster than that. And this right here, there is no problem with this. It's still continuous, it's smooth, it's a thing we call analytic. It has no problems at all. This y squared, you look at it, doesn't look like there's a problem. But the thing is that because there's a y squared right here, it actually causes it to blow up. So if you were to draw a little rectangle right here, and you start with an initial condition here, as long as your function lives in this rectangle, as long as it doesn't escape the rectangle, you'll be fine. But once it leaves the rectangle, you don't know what's going to happen, because what can happen is that eventually, within a finite amount of time, you can blow up. You can have an asymptote like right here, and then it goes to infinity in finite time. So let's continue. Here's an example of where there is a problem. Even though the function looks nice, we're going to see that there's a problem with uniqueness. So I'm going to pause and draw some. So I wanted to briefly mention something that happened with the previous example before we go over this. The thing that's pretty interesting is that when you draw the phase line, it has one critical point at 0. So this is equal to 0. And then it's always positive. Now, because there's existence and uniqueness of solutions, if you start down here, you go up right here, and then you slowly converge to 0, and you last forever. But if you go backwards in time, you actually fly off to infinity before infinity, you actually fly off to infinity. So you can imagine eventually reaching infinity in a finite amount of time because your speed blows up. And that's what's going on with a solution like this. When you start here, you can go backward as long as you like, and you get slower and slower and slower. You slowly converge to this point. That's if you start here, you go backward in time, you slowly converge to 0. You never actually hit 0 because there's a uniqueness. 0 is a solution, so you're never going to actually hit 0 because there's uniqueness. But if you go forward, you will actually quickly blow up in a finite amount of time. So before another second, you'll hit infinity. And that's what is going on here when you have this asymptote. You go up and this is time right here, and you're going like that. So I just wanted to briefly sketch that. Let's go back down to here. Now let's look at this solution here. Oh, I forgot to say that if you start here at 0, you stay there forever. So if you start here at 0, then you just stay here for 0 forever, forward and backward in time. So for this example right here, we can look at the direction field. So solutions can, if you start here, you can go on 0 forever. Or you can all of a sudden decide, oh, I just want to become positive. And then you curve up. So see here, these solutions actually cross. When you plug in x equals negative 3/2 c, this thing becomes 0. And you can start up here with this initial condition. If you go forward in time, it's fine. Once you go backwards in time, you can actually hit 0, and then you hit the solution here. And so you can continue backwards on the 0 solution. That's what you have to go this way. But if you're going forward in time and you start at 0, you could then stay 0 forever, or you can stay 0 and then become negative, stay 0, or then become positive. And it doesn't have to be this point. It's any time you could start. You could decide to not be 0 anymore at any point. You could start here and then go off this way, or you can start here 0 and then become positive, start 0 here and then become negative, or 0 here and then be positive this way. And if you can see this in the phase line, so let's draw the phase line. So here's 0. When you're below, you're negative, and when you're up, you're positive. You can see that from here. So what does this look like if you look at the solutions? So if you start here, the arrow says you have to go up. Because there is existence and uniqueness up here, that's what we see. These curves don't seem to cross. That tells you that there's only one way you can go up. Of course, you can only go up, but maybe when you go up, there's different ways to go up. Because of uniqueness, you have to go up at a particular rate, which isn't specified by the diagram. It's specified by the differential equation. So you could just keep going up. Here, similar, you could just keep going down. However, because there is an existence and uniqueness problem at when y equals 0, we'll see why in a second. You can see, you can continue this way, you can go this way. What this tells you is that if you start here at 0, you can stay there forever. However, you don't have to, because there's a uniqueness problem. You could stay there for an hour and then decide you want to fly off. Or you can stay here for 5 minutes and then decide to fly off. The point is that there's an existence and uniqueness problem at 0, so you don't really know which way you're going to be forced to go. I mean, you're not being forced to go anyway when you start at 0. When you start up here, then you're forced to behave a certain way, because there's uniqueness up here and there's uniqueness down here, but not here. Not here. And where does this problem come from? It comes from the differential equation here. If you take this as f of t comma y, if you take the partial derivative of f with respect to y, this is y to the negative 2/3 times 1/3. And this right here is not continuous when y equals 0. So before we saw that if f wasn't continuous, then we had problems. When f wasn't continuous, we could have existence problems, we could have uniqueness problems, or both. For here, we had f continuous, and we always have solutions, but there's a uniqueness problem. Now let's see, it's not only not continuous, but it also blows up to infinity. When y goes to 0, partial derivative, partial y, goes to plus or minus infinity. It depends on whether, oh, it's always positive, actually. Never mind. Positive infinity. because of the 2 here. So let's see another example. So I'm going to sketch some solutions here, and then we'll talk about it. So what do we have here? Well, we have here, if we start at 0, then we stay here 0 forever. If you start up here, you go up like this way. Start down here, you go this way. But if you look at these pictures, they actually look a little familiar, and they should look familiar based on the solution. So you see here is y equals 0, it's a constant solution. But then here you have exponential solutions when you start up here. When you start up here, you have exponential growth. When you start down here, you have exponential kind of growth. It is increasing, but it's going towards 0. So what we have here is y prime is y when y is bigger than 0, and y prime is negative y when y is less than 0. So here you have the e to the x solutions, and then here you have e to the negative x solutions. However, you see that there's still, even though it's broken up in these 2 different ways, the solutions are still unique. They don't cross each other, and they look like there are always solutions. If you start anywhere, you could just keep going. There's no problems with infinite slope, no problems with weird things like that. And if you look at this, this is continuous. So f of t comma y, that's the value y, this is continuous. And if you do the partial derivative with respect to y, well, this is a little messy because when you graph this, it's like this. It's the absolute value function. So this is plus or minus 1 if it exists. So at this corner here, the derivative doesn't exist, but everywhere else it's -1 and 1. So what you see from this is the derivative here, even though it's not continuous, it still is somewhat nicely behaved. It's still 1 or -1. It's not getting too big. In this example here, it got really big, because when you plug in y equals 0, this blew up. So what we see is a whole bunch of different situations where we can explore uniqueness and existence. Here is the general theory, the theorem about the result. So let us look at some things here. So here's just this general statement, and so we're going to look at what it says. So you have differential equation here, and we're going to look at some initial condition. So let's first draw a window that this is talking about. Tmin, Tmax. I'm going to draw Ymin and Ymax. And so from these 2 things, we get a window. So restricting y in here, and x has to be, ooh, that was terrible. X is going to, I mean, t, the independent variable, is going to be restricted in here. So we get a rectangle in here. Now suppose that we have an initial condition that lives in this rectangle. So we have apologize for that. Suppose you have t naught, y naught, and this is going to be some point here. Now what we're going to do is look at the solution. What do we expect the solution to look like? Well, if our function f is continuous in here, in this rectangle, and the partial derivative of f with respect to y is also continuous, then the solution is going to exist uniquely in this interval, in this rectangle. Maybe outside the rectangle, you have crossings or non-existence. Maybe there's asymptotes. Maybe you have vertical slopes. So basically the slopes blow up, but the function doesn't. But in this rectangle, if you just look at this rectangle in here, because you know f and partial derivative of f with respect to y are continuous, then there's not going to be a problem in this rectangle. You don't know when it's going to leave the rectangle. So you have an interval down here, a to b. In this rectangle, in this interval here, I, a to b, you know that the solution is going to be nice. You don't know when it's going to leave the rectangle. Sometimes you can look at the differential equation and get an idea of when it's going to leave the rectangle. But just from this very general statement right here, you don't know exactly when it leaves the rectangle. So you know that the existence of the solution and its uniqueness are going to be guaranteed in this little interval, but you don't really know much more than that. And if you were to go up and look at all these other examples that we had, you could explore those types of examples. Those types of properties. So I really recommend doing that. So for this example, if you start with this little rectangle here, things are nice when you're in here, but then you leave. How long it takes to leave? Well, you're only given a little rectangle interval where you're guaranteed there is a solution. But once you leave the rectangle, bad things can happen. You can have an asymptote, but bad things might not happen. You go here, you can exist forever this way. And similarly, if you start with, just trying to erase this. Okay. If you go up to one of these examples with vertical slopes, everything is fine as long as you're up here. As long as you don't touch, so I can't draw an infinite rectangle, I should just draw a single rectangle. And as long as you don't leave this rectangle, you're fine. So here, you're always fine because there's no problems at all. But if you start down here, you're fine. You actually find this way. But as soon as you leave the rectangle and hit the really bad part, then problems are happening. We're going to set up the main idea for how we approach numerical methods. There's different ways to approach it, but this is just one way to view it. One way to do it is actually look at the proof of this. So we don't always do this in this course. The proof of the existence and uniqueness theorem. And one way that you do it is you say, okay, y prime is f of t comma y. And well, what does this mean? It's a function that when you plug it in here, you differentiate it. It's the same thing as plugging it over here, where you plug it into this function f. One way to deal with this, if you write it explicitly, is this is going to be f of t, y of t. By explicitly, I mean you're just going to write f, y of t. So I'm writing it in a little more detail. This is going to be the derivative of this. So if you were to integrate this with respect to time, dt, going from t0 to t1, then what would happen here? When you integrate a derivative, it goes away. You just get y of t1 minus y of t0 by the fundamental theorem of calculus. And then this is just some integral here. And this would be really nice if this right here wasn't even here, because then you can calculate what this integral is. So let's see what this is. If f of t comma y, if algebraically you can write it like this. So it doesn't actually depend on y. So for instance, y prime is 2x. Well, you know what the solution to this, it's y is x squared plus a constant c. And you can see that from up here, because if you solve for y of t1, it's y of t0 plus the integral from t0 to t f of t y of t dt. And if you're in this case right here where it doesn't depend on the y, see this right here there's no mention to y in this differential equation, then you could write it like this. Y of t0, which is this thing right here, plus t0 to t1, I apologize, t1, and then f, which is just 2x dx, or 2t dt, because I want to at least be somewhat consistent. And you see right here is that when you plug in t0, this is going to give you 0 here. T1 is t0, the integral from t0 to 0 is 0. And so you get this initial condition here, c. And in general, this is a nice way to calculate. Well, you want to know what this is, you can just calculate this integral. And if you know how to do it algebraically, that's great. But if you don't know how to do it algebraically, you would do it numerically. And that's the exact same idea that's here. We can't actually do these things algebraically all the time. We can't do it in terms of symbols and calculate things in a very nice form. So we try to deal with it numerically. And the same kind of ideas that go into numerical integration are going to be the ideas that go into numerical solutions to differential equations. So let's go back. Let's remember some of the ideas about numerical integration for very simple situations. Suppose we want to approximate the area under a curve to the right, or to the left. Wow, that was terrible. Okay, so you have this function over here from t0 to t1, and you have a function f of t, and we want to calculate its interval. So if you knew what f was, you could maybe calculate this interval exactly. But if you don't know what it is, and you only know some points on it, or maybe it's an expression that you don't know how to integrate, basically what you do is you use some kind of method that calculates it approximately, not exactly. So some of the methods that we saw, left Riemann sum, right Riemann sum, trapezoidal method, Simpson's rule, and we'll talk about an adaptive method in a second. And the idea for these two, I mean, for a lot of these actually, is that you take this interval here and you cut it up into some pieces. And then each time you cut it up, it makes little rectangles here. And then what you say is, okay, this is a rectangle almost, and this is kind of almost a rectangle, and this is kind of a rectangle, and this is kind of a rectangle. Or maybe it's some other shape. Maybe it's not a rectangle, maybe it's a trapezoid. So maybe you approximate with a trapezoid, not a rectangle. And what you do is you calculate the area under these shapes. So these are trapezoids. Here, they're going to be rectangles. But the exact way you calculate the rectangles is where the details are. So for this one, it's the left Riemann sum. So you use the left point to calculate the height of the rectangle. And you see that you're getting too much area here. But here, you're getting not enough area. It's missing all this area up here. Apologize for that. You're missing all this area here. And if you do the left Riemann sum here, you miss all this area here. So these ones are missing area, and this one has too much area. And if you do the same thing over here, but with the right Riemann sum, this one's basically good. This one you're losing area. This one you got too much. This one's too much. Too much. The trapezoidal method is nice because it doesn't depend on the fact that one side might be off a little bit. It kind of balances the fact that, so this one maybe is a little high, this one's a little low, but most of the time you're somewhere in between, usually. So maybe the function is actually very wild and it oscillates like that. But you know, if you pick these step sizes pretty small, then it'll probably be fun. And that's the idea. This trapezoidal method is actually an average of these two methods. So remember actually the formula for a trapezoid, the area of a trapezoid, if you have something like this, if you're using the left Riemann sum, you would just get this area. So let's say this is height 1 with delta t here. And this is height 2 with delta t. So for the left Riemann sum, you have h1 times delta t. For the right Riemann sum, you have h2 times delta t. And if you were to calculate the area of the trapezoid, it's actually 1/2 h1 plus h2 times delta t. You can calculate that using triangles, or if you just remember the formula from like high school. And regardless, you see this right here is actually 1/2 h1 plus h2 delta t. And if you were to write the delta t up here, you see it's actually an average of this area and this area here. But we're actually going to leave the delta t down here because this number right here is an average of h1 and h2. And this is going to be more analogous to the method we use later. Another method we could use is Simpson's rule, something you learn in Calc 2 a lot with these other methods too, is that you can do a similar sort of thing. You cut things up, but instead of approximating with a trapezoid or with a rectangle, you approximate with a best fit parabola. So you look at, for this point right here, you look at these 3 points and you say, okay, what's a parabola that passes through these 3 points? Terrible looking parabola. But you only look at this part right here. And I guess it depends on exactly what you're doing for this method. But the idea is that you can calculate the area in these regions using parabolas. And so that's Simpson's rule, which is a generalization of these sorts of methods here. Another method you might try is you might say, okay, no matter what I'm doing, if I'm doing one of these methods up here, for instance, or method like over here, you might say, well, where it's flat, whatever method I use is probably going to be pretty good. Sorry. So I could pick a width here. So T0 to T1, it's pretty wide. But it's the part where the function is growing pretty quickly that I need maybe smaller rectangles. Not quite so much down here. But when it's growing quickly, I might need smaller rectangles to actually get very careful. But once it flattens out, I can use wider rectangles. This is like an adapted method where it looks at the rate of growth of the function and then deals with some of those problems that are caused by the growth. So you see here that there's problems being caused by the growth of the function, but where the function is very flat, there's not really a problem. It deals with that by choosing different step sizes. There's not a constant step size. So this one here, some of the step sizes are very small and some of them are bigger. So one way to start looking at the way that you can think about these kinds of methods, these kinds of ideas, breaking something up into small pieces and then putting those small pieces together, is to look at Euler's method. It's a very simple method. And the idea is pretty simple. Suppose you want to go from this point here, this is 0, 1. Oops. Let me get a bigger pen size so it's easier to see. So you just go here and you want to go all the way to 1. And let's see, the differential equation in this case is 2xy minus x. So for this differential equation, I want to see what the solution looks like. Well, I can kind of guess what its solution looks like, something like that. So a guess is that y of 1 is about 1.8. It's just a guess based off just my freehand drawing. One way to be a little more precise is you can say, okay, I want to do the thing I was doing there, but I do it in step sizes. So I say, okay, what is the slope here? Well, the slope here is 0. So let's pick some step sizes first before I get carried away. So this is going to be T0 is 0, T1 is half, and T2 is 1. And so these are what I'm going to get from Euler's method. So I start here at 0, and the height here is 1. And then how do I calculate time t is a half? Well, what I could say is, okay, the slope here is 0. So I can use this slope to go to this next point over here. So I just walk all the way over here, and I get half here. I mean, sorry, I apologize. I still have height 1. And then here, I use height, whatever the slope is here. I use this slope right here to calculate the height. So I walk this way to get about 1.4. If I want to calculate exactly what it is, well, what I do is I calculate y prime at this point here. It's going to be, I'm using t here, so maybe I should just stick with t. So we're going to do later in the demonstration. So at 1/2, and then height 1. So I just plug it into this expression here. 2 times 1/2 times 1 minus 1/2. So this is 1 minus 1/2, which is 1/2. Which means when I step over 1/2, that means that delta y over delta x, I mean delta t, because I'm going on a straight line, is 1/2. That's the slope. Delta t is 1/2. That means delta y is 1/4. So 0.25. So I've increased by 0.25, which is back here. So if I were actually following it carefully, I would have gotten 0.25. So if I used Euler's method with a step size h is 1/2, which you see there are huge jumps. then I get about, not 1.4. That was just based off my picture, about 1.25. That's the exact number that I got. And you can do this with a different step size. So let's do that. So you say step size is going to be 1/4. Now for the picture for that, it's going to look a little different. So let's go down. So step size of 1/4. So here's 1, here's 0, here's our starting point. So what I do is I break this up into 4 pieces. So this is going to be 4. I mean, the difference is 1/4. So the number of pieces is going to be 5. So this is a 4th. This is a 4th. Going to 7/5, which is about here. So I'm just going 0.25 this way. Ooh, this first one was wrong. That was about 3. 2, 5, 5, 7.5, and then 1. So here's the step sizes. And what you do is you follow this way, you go this way. Let's actually just do it here exactly, instead of just doing off the picture. The idea of the picture is you go here with the slope, you find out what the slope is here, then you keep going this way at that slope. Then you calculate the slope here, and you go this way with that slope. Then you calculate the slope here, and you go this way with that slope. It's a very rough sketch for what it looks like. But if you're going to do it exactly, we should probably just do it that way. So we have t and y. So we start off at 0. We had at height 1. So when we go forward to 1/4, let's just write the times down. 2/4, which is half, 3/4, and 4/4, which is 1. So we can just calculate what these things are. One thing we want to write down is how can we calculate the y from the derivative, which is kind of messy. So let's actually write this here. Y prime. That's one thing we're going to need. And another thing is, how can we find the y from the t and the y prime? Euler's method says that delta y for delta t is going to be, let's number these. So this is going to be t0, t1, t2, t3, t4. This is going to be y0, y1, y2, y3, y4. And these are just derivatives. So the actual, the step size here, the slope that we're going to be using when we go over by the step size is going to be the slope that we got from the previous point. So it's going to be f of, from this point right here. So to be a little more precise, what we mean by delta y or delta t, it's going to be y2 minus y1 over t2 minus t1. That's just going to be the slope between, see, this is going to be t, let's just label them t0, t1, t2, t3, t4, and we go from here to here. This slope right here is y0 here. It's also going to be y1. It's going to have height y1. And then when you go up a little bit, it's going to have height y2, then y3, and y4, something like that. I don't know exactly where they are yet, but that's the point of the method. So y1 minus y0 over t1 minus t0 is going to be the derivative calculated at the previous point. That's this point here. So it's going to be at t0, y0. And the slope going from 1 to 2 is the value from t1, y1. It's the slope calculated here is the slope that you use to get to the second point, t2, y2. And the slope at 3 is the slope that you use to get to t3, y3. So in general, yn plus 1 minus yn over tn plus 1 minus tn is f of tn yn. And now what you see here is if we have a constant step size, this tells us that is a constant h, small step size h. And what we want to do is find the height that we get to by following the slope. So we say that we're going to solve for yn plus 1. We first move this thing over here. F of tn yn. This thing is just h, so we just write h here. Then we solve for yn plus 1. So yn plus this. So you can see that this right here is the next value. This is the previous value, and this is the slope that you have to follow it. And this is your delta t. But delta t is the same in each step, so we're just going to replace it with the letter h. So now we can use this recursive. This is a recursion. We can use this recursive relationship to calculate all these slopes right here. So let's just copy this table, and we'll go down there and do that. Okay, so here we have this. So we start with y0. We start with, this is t0, y0. So to find y1, we just plug in n equals 0 into this relationship here. Because this right here is 0 plus 1, it's y of 0 plus f of t0, y0 times h. y2, so once I know y1, I can calculate y2. It's going to be y1 plus f of t0. I apologize, t1, y1 times h. y3 is y of 2 plus f of t2, y2, h. And then y4 is y3 plus f of t3, y3 times h. So you just calculate each of these. If you were using a computer, you would write a for loop with this kind of expression here. But if you're going to do it by hand, you have to do each step by yourself. That's what the for loop does, basically. So what is f of t naught, y naught? What is the expression for this right here? Not t naught, y naught, but just in general. What we do is we take this ugly expression, definitely should start with something simpler, but that's just what we're doing. So we had f of t, y was 2ty minus t. So if we calculate, so I'm actually going to calculate this one right here and this one right here, and I'll pause for an exercise and let you guys calculate the rest too. So let's say y1 is y0, which is 1, plus this value right here. So it's going to be 2t naught, t naught is 0, times y naught, which is 1, minus t naught, which is 0, times h. H was our step size, which is a fourth. You see it's a fourth. So this is 1. Everything here is 0 times 0, 1/4, which is just 1. So we see y1 is 1. And that right here makes sense off of our picture here, because the slope here was horizontal. We don't actually go up at all when we go over. Now let's go calculate y2. So what we do is we just use this expression up here. y1 was 1. And then we're going to plug in the derivative, and then we write in our step size. So the derivative is 2 times the t times the y minus the t. So the t right here is, now we're going to use t1 and y1. So t1 was a fourth. That's a fourth here. And y1 was 1. So it's 1 here. And now you see everything doesn't cancel this time. So we get 1 plus. So let's see. 2 times a fourth is a half. Minus a fourth. So we get 1 plus 1/4 times 1/4, which is 1 plus 1/16. And this right here is about 1. But if you're going to calculate it, You can see that the value is about 1.062, whatever. Just going to put approximate. And you see that because the slope here is very small, it's a fourth, and you're only going over by a fourth, the slope isn't very big. So I wrote 0.062. This right here is about 1.1, which means that when I drew the picture, I made this slope a little too high. And you can tell based on looking at the slopes here. See the slope right here. So if this is 0.1, this is 0.062, which is very small. So what you do is continue with these kind of calculations. So I'll give you guys a second. Just pause the video and calculate what these two are. So now that you've done that, we can just continue doing that. So this right here is 17/16. There. So if we're going for 3/4, you do the previous value. So let's see here. Y3 is Y2. So 17/16 plus the derivative times the step. So the derivative is ty minus t. So what is the t in this case? Our t is 2/4, which is half. And what was the previous y? 17/16. And this is kind of unwieldy, but we can see what this is. So if you calculate this exactly, you get 77/64, which is about 1.203. I'm just using MATLAB to calculate that. For this next one, use the same exact format. Use the previous point. Apologies, 74. And then you add the derivative of the previous point times the step size. So this is 2t. So what is the t of the previous point? It's 3/4. Times the y, which was 77/64. And I'm going to calculate that. And what you see that this is equal to 751 for 512, which is about 1.4668. So let's just say 667. And so what we did is we found out what these numbers were. So if you wanted to, you could plot them. Just go like this, go like that. Very rough estimate. And so what you would do typically is that you would run all these things in a computer because you don't want to do this every time. This is not something you want to do. On the lab, you will explore how to write this with a loop and how to graph these and do some of these other things. So let's actually go to a demo. I could show you some of that. So you see with this demo here, you can enter the differential equation. You can choose your step size, delta x, and you see that it graphs the solution numerically. And here are the calculations that go into it. So here's our step sizes, each increasing by 0.25, a fourth. And then here's our y values. You see, remember we had 1 and then 0.06, which is very close to 1. That's why it actually says 0.1 because it's rounding. 1.2, and then it was 1.668 or something, and it's just rounding up. And if you do this in a computer, you can calculate all these numbers, all the numbers you wouldn't want to do in real life. So it's very interesting. You can change the step size and see what happens. The step size gets bigger. It's becoming less and less like a solution to a differential equation that you're familiar with. If you make it smaller and smaller, it looks more and more continuous. It requires more work. So step size 0 doesn't actually mean anything. It requires more work, but it looks nicer. Another way to look at it, this is a demo where you can compare Euler and Runge-Kutta. I always mess that name up. So this is the actual solution in blue. And if you increase the step size, it gets even worse. You decrease the step size, it's getting better and better. It's just taking a long time. You go to Runge-Kutta, it's almost perfect with this big step size. And we'll explore that more later in MATLAB. Yes. So let's go to Euler step size solution, this demo right here. And you can see actually the step size. So the slopes are, delta y over delta x. So you can see this a little more visually. See the triangles get smaller, and the triangles are going to better approximate our curve. But it still takes a while. Basically what happens is once you get a little bit of error, the error starts to compound. So the original function has like no error, and so it's increasing in a way that's steeping up higher than the other one, because when you use these step sizes, some of the growth is lost. When you go from this point here around 0.7 to 0.7, 1.3, and you go up, you're losing some slope there because the real function actually curves up with a slope that's constantly increasing, but Euler's method only tells you to increase with constant slope on a small time step. So you're actually losing some of that growth, and it's comparable to how continuous growth, like we can actually look at compound interest too. This is a compound interest formula, or let's not do 2, that's too big. Let's just do y. 1.4 or something. I just want it to look reasonable. Okay. And what you can see here is that if you have a small step size, which means few steps, a single step is like simple interest. And then as you increase the step, you're compounding more and more continuously. And you're eventually going to converge to the actual continuously compounding interest. But you can see that some of it is being lost because the slopes are never increasing the whole time. The function is actually increasing the whole time, and the slope is increasing even more. But on each step, you don't have that much more increase. So you can fool around with these demos. We're going to go back to some of the more theory. Okay, so we have the formulas here. There's a whole bunch of k's, and I'm saying that the slope is going to be a weighted average of these k's. So it's kn1 plus 2kn2 plus 2kn3 plus kn4 all over 6. So kn1 is going to get 1/6 weighting, and these two ones are going to get 1/3. It's going to have 1/6. Going to have 1/6. And so first we have to kind of get an idea about where these k's are coming from to really appreciate what's going on. So that's the slope here. So we have this point here, and we want to decide, how do we calculate the slope? Well, one way is we can use Euler's method. That's the slope here. We just calculate what the slope is here. This right here says we walk forward by half a time step. So suppose our time step is 1. Why our time step would be 1? That would be terrible, but we're just doing it so we have enough space. So our time step, total time step, h is 1. Also, sometimes I write delta t. So what we do is we walk forward by half a time step. That's here. Then we go up using Euler's method slope, using that time step. So we go over by Euler's method slope. And then we use both these points. So that's this point here. And we find the slope here. That's the slope here. So this right here has slope kn1. This here has slope kn2. Now, how do we find kn3? What does kn3 do? Well, we still go over by Tn plus h over 2. And then instead of going up using the Euler method slope, we go up using this slope that we just calculated. So we go up with this slope. So that's about up here. that is actually not a good depiction of the slope. So let me just try to get it better. Like that. So if we went forward, we get up here. And now it's this slope. Try to get it. This slope right here is the slope kn3. And then we use that kn3 to calculate this slope. And it says we go a full time step instead of half time step. So a full time step here. And then we go up using this slope that we just calculated. So it is steeper than the other slope. Just a little bit though. So getting over here, we may be up here. And so what we do is we have this slope here. So this is k and 4. So what we did is that we used 4 different points to calculate slopes, all in different spots. So it's not just the slope here, it's also the slopes all around. And we were able to then calculate these different slopes, and then we do this average here. And so keeping that in mind, that this method uses Runge-Kutta, we just explored, that kind of makes sense why, even though we've somehow crossed over the other side, or we've bounced away, even at the points that are not near 0, we still have bad slope. We still have these corners. Basically what happened is Runge-Kutta is calculating the slope of what the next step should be using what it projects it should be using Euler's method. So here at this first corner, the one that's at about height 0.8, it knows it needs to go down, and then it's using the slopes that are near y = 0. And then those slopes are very big, and so it's having problems. It's actually going down, so yeah. So you can see some of the interesting things involved. It's very interesting to fool around with. If you decrease the step size, you still get these problems. Maybe that's too small. But it's very interesting to see exactly what happens with these step size. It's very interesting. It's fun to play with. So I'll let you guys do that. And this is the end for a discussion about numerical analysis in terms of the theory. We're going to go over to MATLAB and explore some of that. So here we have MATLAB. So what we're going to do is we're going to explore how to use ODE45 to solve differential equation numerically. So first, let's just say what our differential equation is going to be. We can do this in here. This is my script. So the y prime is 2ty minus t. So I can solve it symbolically. So I'm defining y as a function of t. Oh, it's sims. I apologize. And so you have sim yt, and so you can solve it numerically using dsolve. So I want the derivative of y to be equal to 2 times t times y minus t. And so I have a solution here. See, this C1 here is going to be our arbitrary constant. It comes from however method you solve it. Basically, in order to actually get a specific solution, you need to use the initial condition. Y of 0 is 1. So I can feed that in here too. Y of 0 is equal to 1. And then I have this solution here. I think before, when I wrote it in OneNote, I forgot to divide by 2. So here is the solution. And this is given by some kind of function. So let's define an anonymous function. So it's going to be a function that takes, I apologize. So y is going to be my anonymous function. It's going to be the actual solution. And what it's going to do is going to take in the value of t, and it's going to spit out the exact solution. So actually, to illustrate something that can go wrong, I'm going to forget this, and I'm just going to copy this in. E to the t squared over 2 The first error I get is that it doesn't recognize e, and the reason is e is just a variable. E is not being treated as a number. So what you have to do is actually use exp, the exponential function. E is just going to be a variable. It can be anything. You can call anything you want e. Like I used y to represent a function, I can use e. It doesn't recognize e as a number like pi. You have to do something else. So here is yt, and this is just some expression. And this right here is not a function, this is an expression. And the reason is I define t up here symbolically. So t is defined symbolically, so this right here makes sense. It's already defined. But if I clear t, now I remove t from the workspace, so t is not over here anymore in the workspace. So what you see is that when I do this definition here, I'm going to get an error because it doesn't know what t is. I didn't tell MATLAB that t was an input variable into this function. So the way that I do that is I do @of, and now I've defined it symbolically. So this is a function handle. This is a way that I can give MATLAB a function without telling MATLAB run this function. It's just like if you have something like Alexa, and Alexa is listening to your conversation while you're speaking, and you say Alexa in your conversation, Alexa might pick it up and think that you're talking to Alexa. So basically what a function handle is a way of doing when you define a function like this and other functions that you have, like if I have ODE45, it thinks I want to run ODE45 if I just call it. But if with the @ symbol, it understands that I'm just referring to ODE45. I'm not actually using it. I'm not telling MATLAB run ODE45. And speaking of ODE45, let's use that. So we don't know how to use it, so let's just ask MATLAB to help us. What does ODE45 do? So this is just some information. This right here is a little too general to appreciate. It's best to see by an example, but this is a general place to start. I go to documentation, and this right here has an example, but let's just use our example up there. So what we're going to do is, if you call ODE45, what you need to do is pass it in 3 things for the basic functionality. You need to pass it a function, you need to pass it some length of time it needs to solve the differential equation on, and you need to pass it an initial condition. So what function should we pass it? Well, we haven't defined a function, so how could we define a function? So this is going to be our function of 2 variables, t, y. It's important that you have them in the right order. 2 times t times y minus t. So this is a function, and I want to illustrate that if you do 1, 2, and f of 2, 1, they are different. And so this is very important to keep in mind, that t is always going to be treated as the independent variable. The first argument is going to be treated as the independent variable. So if you were to define f in the opposite way, when you call ODE45 or some other ODE solver, it depends on the exact implementation of it. But in terms of ODE45 and Quiver 244, like on the previous lab, this thing right here, y, is being treated as the independent variable. So you're thinking t as a function of y, which is not at all what you want. So you actually want to make sure you have them in the right order. So here's our function that we're going to use for our differential equation. So if we go back up to ODE45, and we are going to call it with the function f. Next thing we need to do is pass it a time interval. There's 2 ways to do this. Let's do the simple way. One way you do it is you can pass it the whole interval like this. It's an array. The first one is the beginning time, and the second one is the ending time. And ODE45 is an adapted method. What that means is it's actually going to pick the time interval and timestamps in a way that best optimizes certain things. So it has certain errors built into it. I think it's mentioned up here. There's some kind of errors it's allowed to do. No, it's more in the, oh, here it is. Yeah. So using a default relative error of e, or so 10 to the negative 3, and an absolute default tolerance, 10 to the negative 6. So basically, these are sorts of errors that it's going to allow. And if you use options, You can actually change these errors, make them better, make them worse, things like that. And here are a bunch of other ODE methods. And in this right here, the important thing is that when you have the, apologize for that. So if you have this interval here, if you don't tell it exactly what points to look at, then it's going to pick its own points. And the other thing you need to pass it is an initial condition. So we had y of 0 was 1. So we're going to pass it the initial condition 1. And it seems that what it's doing is it's picking this point right here and using it as the initial time. So here's ODE45 running. And I don't know if you can see this. So let me share the figure. And you see a solution right here. You see that it graphed a bunch of points and it just automatically generated all this stuff. It didn't tell you anything about the numbers, it just graphed them. If you don't want that, what you should do is tell MATLAB exactly what you want. So we should go up here and run it like this, where you give it the time intervals and values at those time intervals. So let's go back down. So let's say T list, Y list. Oops, I accidentally hit enter. And it generated a ton of stuff. So what does it have here? So what it did is it calculated a whole bunch of points. So those points that we just saw graphed, those are these points. 0, 1, that's the initial condition. And then it calculated a whole bunch of time points and a whole bunch of y points, and it lists them vertically. And so you can see these numbers. But one thing you might want to do is graph them, where you might want to compare y to it. So how about we go over here to this script over here and we start plotting some stuff. So we have y. So this right here is a script. And what it is, it's just a whole bunch of code that MATLAB is going to run all at once. So basically, I'm running it over here in the command window, storing things in the workspace over here. But as long as I don't write clear all or something like that, where I clear everything out that I've already done, it's still going to assume that all that's been done. If you look at the beginning of your labs, it actually has clear all and CLC and another command to wipe everything clean before you run the whole script. That's to keep any errors from coming from something else that you did previously. But because I don't want those errors to go away because I didn't do anything wrong, nothing that I haven't fixed, like this is a mistake. So what I can do is I can plot. So let me just do, hold on. So I don't remember exactly all the plot stuff. I mean, I do, but I'm just illustrating it. I'm going to ask MATLAB for help. How are all the different ways I can plot things? So the things I was looking for were these colors and nice designs. So I know that if I plot the T's, T list, Y list, this is going to plot all the numbers that MATLAB generated using ODE45. But I also want to generate, I want to draw it in a way. So because I'm thinking of them as individual points, maybe I'll use stars. So star. And I like cyan, so let's use C. So now if I run this, it's going to generate those things. Okay, so I have my first one here. I don't need to put that. Let me just make a little more space. This is my first plot. I'm telling MATLAB to hold on so I can plot the actual solution. And what is the actual solution? Well, I have T list. And I want to apply my actual solution, the solution to the T list. And before I start, I just start figure. Just it's a good habit, just in case you have anything before. So let's see what happens. Is there an error? There is an error. So what it did, let me show you what it plotted. It plotted this. And these are actually the solutions that we got from ODE45. So I don't see the actual solution. So we're going to have to go back and see what happened. So the thing that happened is we have to look at this error. Error using arrow. Incorrect dimensions for raising matrix to a power. Check that the matrix is square, etc., etc., etc. It says the error was in this thing. This is our definition of why sol. And it occurred in this calling of plot. So what happened is we call plot. This line, we got to line 5. It was fine with this. It was fine with this until we plugged in t-list into ysol. And the reason is that if you have t-list, it's a long list of numbers. If you square it, it doesn't understand what that means. If I do t-list times, because remember the solution ysol, what is ysol? It has a squaring in it. So why aren't you allowed to square a matrix? I mean, an array. Basically what it does is it treats this as a matrix. And in terms of matrices, there's a certain meaning for what it means to square a matrix. We'll talk about that later in the course, but squaring a matrix is only a thing you could do if it's a square array, if it has the same number of rows as columns. And since that isn't true for this, because it's just a long array with many rows and one column, this is not allowed. If you want to square each entry, you have to put a point. And now it's squared each entry. So for instance, to see it a little more clearly, so you have TS, a whole bunch of T's, 0, half, 1, and you TS point squared. And you see that that's these numbers squared. So in my solution for ysol, my definition, I mean, go back up and see here for f, it somehow was, this worked out too. This was fun. You got to be careful though. It's usually good to put points. ODE45 didn't have a problem in this case. So let's go back up to our definition of ysol, which was a long time ago, but here we go. And let's just put points here. So this now should be fine. So if I run this script here, and what we get is exactly what we expected. So let me share that with you. And you see how the figure number is changing each time. So now it's figure 3. The reason is because every time I run the code, it says figure of, and it creates a new figure. So let's just see this. So you see that the starred answers, the ODE45 is very, very close to the actual solution. The question is how close? So how about we zoom in and explore? Let's just pick one of these. And you got to be careful because the width of this thing is going to stretch it out the curve. So I'm just zooming in a whole lot of times. And if I want it to get steeper, it's the shape of the rectangle. Aha, so you see that it's separated. So let us see. So what we can do is write down this number here. 1 point, maybe not write it down. We see is that, let's just look at how many decimal places are right. So the graph at 0.9 is about this number here, the third number from the bottom. And where do they differ? They differ between, there's a 3995 and a 4005. So the decimal places are right for 1, 2, 3, 2, 3. So 5 decimal places, they're correct, which is pretty good. And it's the kind of thing that when you zoom out to a reasonable scale, you can't even tell the difference. So let's go back to MATLAB and see this more specifically. So first of all, in order to find that value that we had, so the value that we zoomed in on is, fortunately, I do not remember what the number was. It's being recorded, but I can't remember. It was, I think it was 0.9. I think that was the point. So let's look at t-list. 0.9 is this one. Unfortunately, I don't remember what entry it is. So let's see. That's not quite right. 0.9, so maybe 39. Okay, so T list 37. That's the 37th entry. Now, if I'm going to find the Y value, I do Y list, which is all the numbers that ODE45 generated, and I plug in 37. So this is my number. And then I want Y sol, the actual solution. And I'm going to plug it in to that same T list value. And I get a number that looks exactly the same. And the reason is because MATLAB's not showing enough decimal places. So I'm going to tell MATLAB that I want to see more. So I'm just going to run these lines again. And let's see. They agree up to the 5. And then they differ off of that. So what we got here is from the picture, we were able to zoom in because it's a nice plot. You're able to zoom in on it. But here you can actually see the numbers. And let's go back to normal format. So whenever I run one of these numbers, they're short again. So the absolute value of the error. So this is going to be Y list of 37 minus Y of T list of 37. This is the absolute error. And what happened here? Oh, okay. So what happened here is I'm not allowed to. Oh, I have Y of it. Remember how I defined Y earlier to be symbolic? All the way at the top here. Because I wrote Y instead of Y, it's not understanding. It's treating this symbolically. It's not plugging it in because it doesn't know what Y is anyway. If I plugged in 37 here instead of T list 37, you're going to get an error. I mean, it's not an error, actually. The reason is that Y sol is this function, e to the t squared, basically. And if I plug in the number 37, I'm basically getting infinite. You got to be careful because this right here is the 37th entry of a whole long list of Y values that ODE45 calculated. And Y sol needs to be calculated at that same value of T. 37 is not the same value of T. So that's why we have to go back to our original thing we had, but with Y sol. Okay, and here is the error that we got. This is the error, the 37th entry. So it says about e to the, 10 to the, sorry. So just having trouble wording it. So if you have this number here, that's 8 powers. So let's look at the numbers again. So although they differ here, this is 399 and this is 400, which is also very close. And then there's a 3 afterward. And so it's actually this spot where the error actually is, where the big difference is. So how many decimal places? That's 4 here and then 4. So that's why there's a -8. So here we got to explore some of the ideas how to use ODE45 and also plotting it using the actual solution. So I thought that I would put that up. Hopefully it'll help you with the lab. So I hope you guys have a nice day and see you later.